Alright, great. So we're going to look at the standard electrode potential. Now, this is quite important if we want to find what the EMF of a cell is. Otherwise, we're going to have to play, let's guess the electrode and hope for the best. Okay, and decide by trial and error what we're going to get as our final EMF, which defeats the object, right? So, the standard electrode potential is for a half cell, is measured under standard conditions. We'll talk about that in a second. When the half cell is connected to a standard hydrogen electrode to form a galvanic cell. So we have something that we're going to compare other electrodes to. So we're going to get a list where we can have what the potential of an element is when it gets oxidized or reduced, okay? But we've got to compare it to a standard hydrogen half cell. Now, you can either stop now and have a look at the video that says hydrogen half cell, or you can do it later, but you do need to watch that at some stage because the animation is very, very useful. So, the hydrogen half cell is a standard, it's called a standard reference cell, okay? It's a reference. They decided to give it a value of 0 because we compare everything to the hydrogen half cell. All right, we have to have a comparison because a voltmeter can only measure a difference. But the values only work if we do it under standard conditions. So, what are those standard conditions? Well, the first one is it must be done at a temperature of 25 degrees Celsius, so that's room temperature. Concentration of the solution, so that would be the electrolyte, okay, must be 1 mole per decimeter cubed. Nothing new here, but now we are working with a hydrogen half cell. That means we're working with a gas. When we work with a gas, the gas must be at a pressure 1 atmosphere or 101.3 kilopascals. Okay, that's very important. If we don't have those standard conditions, then we can't use our table of reduction potentials, which we'll talk about last, and then there's no point in this. Okay, so now this is the setup of the half cell. This hydrogen half cell can either be the anode or the cathode, depends on what the other substance is. Okay, very important. Here we have a platinum electrode. Okay, so we have a platinum electrode for a very important reason. We're working with hydrogen. Hydrogen is a gas. A gas cannot conduct an electric current. So you have to have something that can transport the electrons either away from the hydrogen half cell or towards the hydrogen half cell. So you need to have a conductor, which is why we have platinum. We use platinum because it is inert. It won't take part in the reaction. Okay? Then we have to have an electrolyte at the standard condition of 1 mole per decimeter cubed. That's my electrolyte. How do I get those hydrogen plus ions? We use a strong acid. So here we would use HCl or something like sulfuric acid. Okay, they're strong acids. Why are we going to use strong acids? Because as a strong acid, it ionizes completely. If it ionizes completely, we get lots of ions. We want lots of ions. Those ions then allow us to conduct an electric current. So now we have an option where we can have hydrogen gas, which is going to either become hydrogen plus ions, in other words, get oxidized, or the hydrogen plus ions are gain electrons and they're going to become hydrogen. So, hydrogen gas is pumped into the hydrogen half cell. The hydrogen flows over the porous electrode. At equilibrium, we have an option here. So, we have an option of what can happen. Like I said to you just now, the H plus ions can become H2. The H2 ions can become H plus. This is an equilibrium. We have both. We essentially would have both happening, but one will be prioritized over the other. That depends on what the other half of the cell is, whatever we put at the end. Okay? So, when we look at this, as an example, the copper half cell is connected to a standard hydrogen electrode. So we're using copper as our example. When they connect a voltmeter to the system, we get a voltmeter reading of plus 0.34 volts. This is quite important, okay? That voltmeter reading is now assigned as the potential for copper. We can make use of it. But, I'm saying but a lot. Because it is a positive 0.34 value, it means the copper is less likely to give up its electrons. In other words, the copper doesn't want to get reduced. The copper desperately wants to be, doesn't want to be oxidized. The copper desperately wants to be reduced. So, instead of the copper being oxidized, the hydrogen gets oxidized. So the hydrogen will give away its electrons and become H+. So the hydrogen is the anode. Reduction will take place at the copper half cell because it wants to be reduced more than it wants to be oxidized. So the Cu2 plus ions in the electrolyte will take those electrons and become Cu. But remember, copper can be oxidized or reduced. So we can now write the copper half reaction as an equilibrium when I put the electrode potential values onto it. This tells me that we have an option: copper can be reduced or copper can be oxidized. When I use the copper in a cell, the copper this reaction changes, and it either becomes it either becomes an oxidation reaction or becomes a reduction reaction, and then we get rid of the double arrows. Okay, we can't keep the double arrows. These half cell reactions are listed in a table according to their reducing and oxidizing ability. The smallest E values are the strongest reducing agents. In other words, they desperately want to be oxidized. Lithium is the strongest one that we have. Lithium has a value of minus 3,05 volts. So when I say smallest, I mean smallest like on a number line. Okay? The highest E cell value indicates the strongest oxidizing agent, substances that desperately want to be reduced. Fluorine is our strongest oxidizing agent. It has a value of 2,85, okay, or 75, something like that. But it's positive, okay? So by highest, I mean highest on a number line. Very, very important. How do we use these values to calculate the EMF of a cell? Very important. Well, the EMF is now the E0 cell. The EMF is calculated using the standard table of standard reduction potentials, a very important concept for us. And the equation is given to us as the E cell equals the E cathode minus the E anode. On your information sheets, you're also going to get this as E oxidizing agent. All right. Minus the E of the reducing agent, or it's going to be E reduction minus E oxidation. All of those refer to the same thing. The anode is the reducing agent, and it's where oxidation takes place. The cathode is the oxidizing agent, and it's where reduction takes place. You can use any one of these three equations. It doesn't matter, as long as you do not abbreviate any of the names. You must use the names as given on your information sheet. Without that, you will get it wrong. Okay? In the next video, we will look at how to actually use the table.